Welcome, and thank you for watching. My name is Stephen Casper, and this video accompanies a new paper from the AAAI 2021 conference entitled Frivolous Units, Wider Networks Are Not Really That Wide. Since this isn't live, I unfortunately can't take questions, but if you have them, just email us. We're pretty friendly, and we'd love to talk to you about any questions, big or small, regardless of your level of experience in deep learning. So, as the title suggests, we study how wide networks fail to utilize their entire capacity, and we focus here on what we call frivolous units. We define these units to be neurons that the network does not effectively utilize and which can be removed without changing the function that the network computes, or at least not by changing it very much. Ultimately, this project lies at the intersection of implicit regularization, understanding networks in terms of their individual units, as well as compression. So we think you might like this paper if you're interested in any of these three areas, or fundamental phenomena in deep neural networks, such as lottery tickets or double descent. Ultimately, we find that frivolous units appear in greater proportions as network width is increased, which provides some evidence that implicit regularization operates largely at the level of individual units in these networks. And in addition to offering some better insight on what happens to units as we increase network width, this all comes with a few nice implications for better compression algorithms, better compression-based bounds, and potentially a few clues on how we can study robustness in biological brains. So let's get started. One very interesting phenomenon that is commonly observed in deep networks is that wider ones with more units per layer tend to generalize as well or better than thinner ones when trained on the same task, even without explicit regularization, such as dropout or weight decay. And you may actually be familiar with the double descent phenomenon, in which under the right conditions, network loss initially goes down, then goes up, peaks, and then steadily goes down again as they become wider and wider. Typically, modern networks reside in this over-parameterized regime here in the second descent. And we're interested in better understanding this behavior in these networks. So we ask, what's involved in the second descent? To get some more clues, here are some examples of over-parameterized networks that we trained, as well as their test accuracy. In each of these, we see that accuracy either increases or stays the same as width increases. So why do wider networks not tend to perform more poorly, even as their architectures become more and more capable of overfitting? The means by which models automatically tend towards simple solutions that are more likely to generalize is referred to as implicit regularization. So here we ask, what neural mechanisms facilitate increases in network width without decreases in performance as a result of implicit regularization? We think some clues can come from some recent work on the lottery ticket hypothesis, which has received a lot of attention. So in many networks, we have evidence that the crucial computations that are performed are done by weight-sparse subnetworks with initializations that are automatically primed for the learning task at hand at the beginning of training. It's said that such subnetworks have won the initialization lottery, and in a recent paper, authors Frankel and Carbon develop a method for finding these lottery ticket subnetworks and show that they're often an order of magnitude or more smaller than the original network. In each of these plots, we can see that as we move along the x-axis and the percent of weights remaining even gets pretty small, network performance can still be maintained so long as you're sticking to a lottery-winning subnetwork. Frankel and Carbon suggest that one way that larger networks are able to generalize so well is that they buy more of these lottery tickets and therefore more reliably have a high-performing lottery-winning subnetwork. But what about subnetworks that aren't part of the lottery ticket? This begs the question, why do they not harm performance? We think it has something to do with frivolous features. We look at this from one angle that's largely inspired from neuroscience, the individual unit level. Units have been referred to as the building blocks of interpretability, as analyzing them allows for simple visual understandings. An example work here from Ola et al. Developed visual semantic interpretations of units by optimizing images to activate them. They showed that individual units sometimes serve nice interpretable semantic roles, such as a dog detector or a cat detector. And in fact, we'll revisit this method later in the presentation. But while some units lend themselves to obvious semantic interpretations, most do not. Maybe that also has something to do with frivolous features. And besides, there are a few other clues, which suggest that networks may form units that are frivolous, such as the success of dropout and the remarkable robustness of biological brains to the death of individual neurons. So now let's dive into some details about frivolous units. And in fact, we study two distinct types of them. First are prunable units, which can be removed from a network simply by taking them out. We measure how prunable a network is on average just by analyzing how robust it is to the dropout of different proportions of random units over the test set. Second, we study what we call redundant units, which can be removed from the network by factorizing their layers. We measure these by linear analysis of the activations within each layer across the test set. Now, there are a few past approaches to network compression at the unit level that have targeted some notion or other of prunable or redundant units. However, here we analyze both, and here we focus on preserving network function, aka a mapping from a data distribution to labels, rather than just accuracy, like most compression papers focus on. This is because preserving accuracy is necessary, though not sufficient, to guarantee that a compressed network computes the same function as the original one. So you may ask, what is the relationship between prunability and redundancy? In fact, they can emerge together or independently. And to show you this, let's just look at some simple prototypes in which we build a wide double-width network from a thin one. So consider a network with logits theta transpose u, where theta gives the weights of the last layer and u gives the activations of the units before it. In one example, prunability and redundancy together at the same time could result from duplication of the units and then just making the new weights zero-valued. So here, each unit has an activational twin, hence it's redundant, but all the new units are perfectly prunable, hence prunability has increased compared to the thin network. Next, only prunability without redundancy could result from adding a bunch of new units, which we label V, as long as they have activations uncorrelated to the original ones and to each other, and then again, making the new weights all zero-valued. And then finally, only redundancy without prunability could be achieved by what we call a weight balancing trick. So if we again duplicate all the units and all the weights in this time, dividing by 2, and then if we add and subtract some large balancing term B, then when a unit is pruned, its output changes by an offset which is linear in B, which causes a large change to the network. And not only can we see the distinctness of prunability and redundancy using these simple prototypical examples, we find in practice that some networks develop more prunable units and others develop more redundant units as we increase their width. So to start out, we want to share the results from some experiments we did with AlexNet architectures trained on the CFAR10 dataset. We took a set of networks of different size factors, 1/4x through 4x, and trained some with GLERO, or low variance initialization, and others with HE, or high variance initialization. So first, to test prunability, we ablated or dropped out different proportions of the units randomly as shown along the x-axis. In these GLERO low variance initialization nets, as the width increased, robustness to these proportional ablations increased as well. You can see this by noting the increasing area under the curve as these curves get darker and the networks get bigger. But for the HE networks, which have high initialization variance, there's much less of an increase and not really a consistent pattern. Next, for redundancy, one way of getting a really rough sense of redundancy is just to look at the unit-to-unit linear correlations within layers on the test set. With GLERO nets, we find that the distribution of these absolute valued correlation coefficients doesn't get much more of a tail as width increases. But for the HE networks, there's a dramatic increase. So overall, what we're seeing is that real networks develop prunable and redundant units, and they do so to different extents. We're also starting to see a few clues of things involved in the development of prunability and redundancy, namely initialization variance. And next, we're going to delve into how these units emerge in a variety of networks, and ultimately, we're going to show that wider networks very, very consistently have greater proportions of frivolous units. But first, I just want to get through a couple quick notes on methods. The key things to note are that we use ResNet 18s and Inception v3s with ImageNet experiments, AlexNets and ResNet 56s with CFAR10 experiments, and single hidden layer multi-layer perceptrons, or MLPs, on synthetic data, which we generate using a random teacher network that's given uncorrelated Gaussian inputs. When it comes to prunability, we measure it by randomly ablating or dropping out various proportions of units and interpolating to estimate the number of units that can be ablated this way while preserving 80% of labels. For redundancy, we measure it by doing principal component analysis on activations over the test set and seeing what number of components can be removed while still capturing 95% of the variance among the activations. For these, we average results across layers. So let's get to some results, and I want to start with ImageNet networks. Here, and in all of the subsequent plots, we plot the number of prunable and redundant units we find divided by the number of units in the 4x width networks in order to make sure that all values are between 0 and 1. It's important to be really clear that the values plotted here are normalized counts of units and not proportions of units. Also note that we have both axes on a log scale. So when the network width goes up, of course, the number of prunable and redundant units goes up. This is exactly what we'd expect, but how much is it going up? We plot what we call the G factor, G for gain, which gives the average amount by which prunable or redundant units increase when the width is doubled. So if G is less than 2, then frivolous units increase at a slower rate than the network overall. And if G is greater than 2, then they increase at a faster rate. We see that in all cases, G for prunable or redundant units is greater than 2. This is a trend that will continue when we look at other networks. And in fact, there's a case where G is less than 2 for redundancy in inception V3s, but it turned out to be somewhat of an exception, and it was accompanied by a correspondingly large G for prunability. You may have noticed that we don't have 2x and 4x sized inception V3s in these plots. That's just because they were too big to fit in our hardware, but we trained versions in which a single layer was varied over the full range, from 1/4x to 4x, and that's shown in light green. It's also useful to notice that G is pretty different for prunable and redundant units in both of these network types. So this is evidence of a significant amount of disjointness between the two. Next, we also see what individual layers look like in the Resonate 18s. And we find that these layers follow the same trend of the network as a whole. Notice the slopes are usually pretty similar, but often with different base proportions. And in one layer here on the right especially, there's a pretty big difference. Next, we know that frivolous units by definition are a result of implicit regularization. But how does this relate to generalization? As it turns out, they tend to increase with G greater than 2, even with AlexNets that we looked into, and as well as ResNet 56s, trained on random CFAR10 labels, where there's no meaningful generalization happening. This shows here that implicit regularization doesn't imply generalization, and that the formation of these units, even with G greater than 2, doesn't just depend on regularities in the dataset. Next, we're interested in implicit versus explicit regularization. What about the relation to explicit regularization? Here, we train AlexNets on CFAR10 with explicit regularizers dropout, data augmentation, weight decay, as well as all three together. And we see that although dropout seems to have a noticeable effect, which is kind of what you'd expect, honestly, the trend lines are pretty tight and regular, and so are the slopes. So this gives some evidence that implicit and explicit regularization may be in some meaningful ways doing different things to the networks here at the level of individual units. So you might recall earlier, we showed you that Glaro versus HE initializations, which have low and high variance respectively, in the AlexNets have a pretty big influence on prunability and redundancy. And here are the plots. For prunability, we think it's noteworthy the difference in the 4x models is about a factor of 4. A final interesting trend that we found when looking with the MLPs and synthetic data was that the dimensionality of the data points matters. Here we show two extremes, 10-dimensional data and 10,000 dimensional data. And we plot curves for two distinct levels of weight initialization variance. And when it comes to redundancy, dataset size seems to have a major effect under high initialization variance. We also in the paper have a lot of other experiments, especially in the appendix, and those look into trends in individual layers and other training factors. But these were just the main ways that we found that prunability and redundancy could be influenced that we're showing to you now. And finally, we also want to emphasize a limitation and a point of clarification. And it's that just because G is greater than 2 for one of these plots doesn't mean that the wider networks don't develop any new non-frivolous units. In fact, they almost always do. And we look into this in the paper. Networks tend to gain unit level complexity with width, but it's just not proportional to width. That's what our main finding is. And next, the last big question that we ask is whether frivolous units make interpreting wider networks more difficult in practice. Since wider networks have greater proportions of frivolous units, and assuming that frivolous units are generally more difficult to interpret than non-frivolous ones, then we wondered, do wider networks end up being more difficult to interpret as a result of forming more of these frivolous units? To test this, we look at wide and thin ResNet 18s and Inception V3s, and visualized units within them. Here, we show some examples from the ResNet 18s. We produce visualizations with the Lucid package, which optimizes visualizations via gradient descent. Next, we calculate total variation as a proxy for interpretability. And in fact, here's the formula. You can pause and look at it if you'd like, but ultimately it just measures the total difference in the values between adjacent pixels across an image. The idea is that more interpretable units ought to have visualizations with lower frequency patterns, which correspond to low total variation. We do this for the original images and their Fourier transforms in order to capture simplicity that may exist in frequency space as opposed to pixel space. And those, as well as the original images, are shown here. Finally, we use a permutation-based hypothesis test to get a one-sided p-value, testing the null hypothesis that there would be no difference between thin and wide networks against the alternative that the smaller networks have more interpretable units. And there's a lot to look at in these tables, so feel free to pause and analyze. But ultimately, we don't draw any strong conclusions. We find a little bit more evidence here for better interpretability in thin nets than in wide nets, but trends vary across layers, and they aren't all regular. So we leave for future work the possibility of looking into this with some new methods. To conclude, prunability and redundancy are these two prevalent yet distinct capacity constraining features which help to explain why wider networks avoid performing more poorly compared to thinner ones. From our results, we propose a new hypothesis, saying that all else equal, a tuned wide network will develop a greater proportion of frivolous units than a tuned thin one. We hope that new insights will come from extending or challenging this hypothesis. And some notes on future work and limitations. These findings suggest ways to improve on baselines for compression and compression-based generalization bounds that only consider one of the two types of frivolous units. In fact, one very recent and impressive paper from Zhou et al. Developed non-vacuous compression-based generalization bounds at the ImageNet level, but they only considered prunability. So considering redundancy too could be a natural opportunity for tighter results. Next, this framework we think could also be useful for studying robustness and redundancy in biological brains. And this is a major phenomenon. In fact, it's been estimated that as many as half or more of the neurons in the human brain fall under our definition of frivolous. Next, we're also just naturally interested in how disjoint prunable and redundant units are in different networks trained under different conditions. And finally, while we find that prunability and redundancy are at least necessary to explain non-overfitting in wide networks, we don't find that they're sufficient. And we're excited about work in the future on joint analysis of the two, analysis of non-unit level compressibilities, or causal factors work, which works to connect existing knowledge that we have about implicit regularization to unit level phenomena in particular. And lastly, I just have a lot of nice people to thank, especially co-authors Xavier Boix, Vanessa DiMario, Ling Guo, Martin Schrimpf, Casper Vinken, and PI Gabriel Kreiman. And this research was made possible with support from the Center for Brains, Minds, and Machines, Boston Children's Hospital, the Harvard Undergraduate Research and Fellowships Office, MIT SenseTime Alliance, NVIDIA, and Fujitsu Laboratories. Ultimately, if you're interested in working on any of these questions or related ones, please let us know. We think that'd be really interesting to find out about. And just thanks for listening. Here are our emails. You should have a really low threshold for contacting us. And if you want to get to the paper, here's a quick QR code that can take you there. And if you read, we hope you enjoy. Thank you very much.